Removal of Cr6 from synthetic wastewater by low-cost adsorbent developed from Amla Wood Sawdust, Emblica Officinalis. Abstract. The present study aims to understand the effectiveness of using Amla Wood Sawdust, AWS, for the removal of hexavalent chromium metal and to obtain an optimum condition for maximum extraction. AWS was prepared using waste barks of amla tree, which was then dried, ground and activated to prepare the low-cost adsorbent. Stock solution of chromium was prepared in the laboratory using potassium dichromate and distilled water, and the pH of the stock solution was varied using sulphuric acid. The effects of contact time, pH value of stock solution and adsorbent dosage were studied under batch mode of operation. Experimental data revealed that hexavalent chromium concentration in synthetic wastewater was reduced up to 83.2% at suitable conditions of contact time, pH, and adsorbent concentration. Keywords: adsorption, chromium, 6, synthetic wastewater, Amla Wood Sawdust. Heavy metals. Introduction. The presence of heavy metals in drinking water sources and in edible agricultural crops can be harmful to human. It is well known that heavy metals can be toxic, e.g. they damage nerves, liver, and bones, and also block functional groups of vital enzymes. 1. Heavy metals are found in water, air, and soil. The major sources of heavy metals in water and soil are wastewater streams from various industrial processes. 2. Heavy metals like chromium, copper, lead, zinc, mercury, cadmium, etc. are present in wastewater from several industries such as metal cleaning and plating baths, refineries, paper and pulp, tanning, dyes and pigments, wood preserving, glass, ceramic paints, catalysis, chemical manufacturing, etc., in which chromium, 6, is present from 5 to 220 mg/dm3, which are discharged into environment 3 to 5. Heavy metals have been used by humans for thousands of years. Although several adverse health effects of heavy metals have been known for a long time, exposure to heavy metals continues, and is even increasing in some parts of the world, in particular in less developed countries. Although emissions have declined in most developed countries over the last 100 years, heavy metals are dangerous due to their tendency for bioaccumulation. Bioaccumulation indicates an increase in the concentration of a certain chemical within a biological organism over time, compared to the chemical's concentration in the environment. Compounds accumulate in living things any time they are taken up and are stored faster than they are broken down, metabolized, or excreted. There are more than 20 heavy metals, of which 4 are of particular concern to human health: lead, Pb, cadmium, Cd, mercury, Hg, and inorganic arsenic, As. These 4 heavy metals are 4 of the top 6 hazards present in toxic waste sites. They are highly toxic and can cause damaging effects even at very low concentrations. They tend to accumulate in the food chain and in the body and can be stored in soft, e.g., kidney, and hard tissues, e.g., bone. Being metals, they often exist in a positively charged form and can bind onto negatively charged organic molecules to form complexes. In the present study, an attempt has been made to study the removal of hexavalent chromium, Cr6, using amla waste sawdust from dried barks of amla trees. Experimental. Adsorbent preparation. Amla wood was collected locally and was grounded to small particles of size 120 to 500 m. It was washed with deionized water for removal of dirt, color, and other particular matter, and then dried again. AWS was then treated with sulphuric acid, H2SO4, by adding 5 ml of H2SO4 to 100 ml of deionized water and 10 grams of AWS. The final mixture was stirred and treated at 305 K for 24 hours till the mixture became thick slurry. The slurry was washed with deionized water and the pH of filtrate was fixed at 5. The final adsorbent was dried and then stored in plastic bags in a dessicator at room temperature to prevent moisture to come in contact with the adsorbent. Stock solution of chromium. The stock solution's chromium ions were prepared using 1.4145 gram of potassium dichromate, K2Cr2O7, in 500 ml of distilled water in a 1000 ml volumetric flask. It was dissolved by shaking and the volume was made up to the mark. Chromium solution concentration of the solution was 500 mg/L. Batch mode adsorption studies. The adsorption of chromium, 6, on adsorbent was studied by batch process. In this study, the analytical grade chemicals were used for testing various parameters in wastewaters. The absorbance and chromium ions of synthetic wastewater were found using UV spectrophotometer. A known weight of adsorbent, e.g. 0.5 to 4 grams adsorbent, was equilibrated with 100 ml of the each chromium ion solution of known concentration 500 mg/L in 12 stoppered glass flasks at a fixed temperature, 303 K, in an orbital shaker for a known period, 30,150 minute, of time. After equilibration, 100 ml sample collected from each flask, in time interval of 30, 60, 90, 120, and 150 minutes. The adsorbent was separated from solution by filtration using Whitman No. 42 filter paper. The concentration of chromium ions retained in the solution was measured by UV visible spectrophotometer. The effect of several parameters, such as pH, contact time, and adsorbent dose on the adsorption were studied. The pH of the absorptive solutions was adjusted using sulphuric acid, sodium hydroxide, and buffer solutions when required. The results of these studies were used to obtain the conditions for maximum CR6 removal from aqueous solution. The %CR6 removal was calculated using the following equation. B. Effect of pH. Optimum adsorbent dosage of 2.5 gm per 100 ml of solution was used and pH of the solution was varied to study the effect of pH of the adsorption of CR6. Different pH conditions were maintained by adding H2SO4 and acetic acid sodium acetate buffer solution. From figure 3, we can see that the maximum adsorption occurred at a predominantly acidic solution with a pH range pH 2 and 3. However, any further increase in pH lowers the potential of adsorption significantly. Where CO, initial concentration of test solution, mg/L, CE, final equilibrium concentration of test solution mg/L. The effect of adsorbent dosage, pH, contact time, initial concentration of CR6, and temperature were studied by varying any one of the parameters and keeping the other parameters constant. Results and discussions. A. Effect of adsorbent dosage. The adsorbent dosage was varied from 0.5 to 4 grams per 100 ml of stock solution. From figure 2 we can observe that there is a linear increase in the removal of CR6 with increase in adsorbent concentration. The linear rise however reaches a maxima at 82% removal at 2.5 gm per 100 ml of adsorbent dosage. Beyond the optimum dosage, there is no noticeable increase in CR6 removal, which indicates that 2.5 gm per 100 ml is the optimum adsorbent dosage for the removal of CR6. This optimum dosage F adsorbent was used for further studies to observe the effect of pH and contact time. See effect of contact time. The time required to reach equilibrium for adsorption by AWs is shown in figure 4. The adsorption of chromium was dependent on pH of aqueous solution and increased with decrease in pH of CR6. The contact time was varied between 30 minutes to 150 minutes. The rate of adsorption increased at lower contact time and then it reached equilibrium at 100 minutes of contact time. At this condition the maximum removal of CR6 was observed at 83% for a dosage of 2.5 gm per 100 ml stock solution at pH 2. Conclusion. The effect of adsorbent concentration, pH, and contact time on the removal of CR6 from wastewater shows the conditions at which maximum adsorption occurs and also gives some insight into the underlying mechanism of the adsorption that occurs. Beyond the optimum dosage of adsorbent in the system there is no significant increase in the adsorption rate. This indicates that at higher concentration there is no increase in active sites, but the excess adsorbents are carried out of the system without being used. The study also shows that the adsorption rate is dependent on the surface charges that are present in the system. At lower pH, there is an increase of H and in the adsorbent surface, which tends to attract the Cr6 particles, thus leading to an increase in the rate of adsorption. The optimum contact time was at 100 minutes for the optimum dosage and pH beyond which the adsorption curves flattens. The nature of adsorption can be further studied using the various isotherms to have a better understanding of the underlying phenomena. The present study shows that using AWS we can obtain a maximum removal of 83% of Cr6 at the optimum conditions of concentration, pH, and contact time.